So, hi everyone. Hello. Yeah. So, hi everyone. So, I think our scheduled time is from 3 p.m. to 5 p.m. So, let's just wait for 5 6 minutes and let's wait for other participants to join. We'll start after that. People are still joining in. So, I typically start at 3 5 p.m. So, to accommodate everyone. So, let's just wait for 3 4 minutes and I think we can start with that. So it's already 4 minutes past 3. I think we can start, and requesting everyone to please turn off their microphones. Yeah, that would be better. Thank you. People are still joining. Actually, it's first week, so anyways, we can start. It's already 5 minutes past 3. It is, yeah. So is my screen visible? Am I audible? Can you confirm? Okay, yeah. Thank you, thank you, thank you. Yeah, so I think we can start. So, good afternoon, everyone. My name is just a second. People are still joining. Just give me a second. So this is the first class. I can understand, but it's open. You guys can join from 3 p.m. to 4 p.m. anytime, 3 to 4. Try to join between 3 to 4, but you'll miss a portion of it. But if you are joining the session, try to be on time. It would be better if you can join at around 3, 3:05. I typically start at 3:05, and so, as a part of our PMR of data deliverables, we are required to perform TA duties, and as a part of that, I have chosen this NPTEL course. So, I'm NPTEL TA, I guess, for the fifth time, but this is the first time I'm for CMOS digital VLSI design. Before that, I was for digital electronic circuits and digital circuits. So, this is the 8 week long course. You guys must be aware of that. So now let me give my introduction first. We are bound to give this every time since new participants come in every time. My name is Musa Rafiq. I'm a PMR scholar, a PhD student in the Department of Electrical Engineering at IIT Kanpur. So I'm a final year PhD student. So typically final year here means fifth year. So I am course TA. Here the TA means I have to. I'll show you the problems pertaining to that week's content, and I'll be solving some problems here live. Uh, and the problems are such that these are aligned with your coursework for that particular week, and it will help in your exams, in your assignments. One thing that is made clear to us is that we are not required to show the problems that are in your assignment. So whatever problems there are in assignments, I will not show them in that week. Maybe some weeks later when the due date is passed, I can show them, but right now I can't show the same problems, but the problems that I'll be showing are somewhat aligned in that way, or maybe give the grasp matlab, bigger picture of it, right? So today we have some 10 to 12 problems. So typically in the previous courses I was having 20 problems, but that courses didn't involve that much of numericals and all. Here I think 10 to 15 problems will be sufficient, and as we go towards the next week when we discuss problems related to CMOS inverters, then the sequential circuits, combinational circuits, here we have the theoretical part of it is much more than the previous courses that I have done. So 10 to 15 problems, I am thinking about keeping 10 to 15 problems uh, that I like you guys to solve. And apart from that, I have some problems that I have marked here. What I typically do is I first ask the students to solve them at their particular place, and once they have solved or they have tried to solve it, I show the solutions. Whatever problems I have shown here, I'll show the solutions of them all. And other than that, is there something else? Yeah, guidelines I'll discuss in the coming slides. So let me just admit. Yeah, and one more thing. Whenever I am solving a problem, I won't be able to admit a new student because I am solving a problem. I'm busy with this annotation. After I solve a problem, I'll admit them. So I'll just lay out the guidelines, and then you guys will be clear with that. So introduction I have given. Now let's move to the next slide. That is the course layout. So this is something that you know. The course content is divided into 8 weeks. This is the week first where the Professor Dasgupta has discussed MOS transistor basics and also touched on CMOS inverter part. But the CMOS inverter part is thoroughly discussed in week two and so on. So what I have done here is I have kept some basic problems overall for this session, week session. I have mostly picked the basic problems that are aligned with the week one's assignment. But from the next week, just a second. But from next week, the level may go up slightly high, and CMOS inverter, the problems pertaining to CMOS inverter will be thoroughly discussed, because CMOS inverter forms the backbone of this chapter. So problems related to that will be thoroughly discussed. And one more thing, this is a problem solving session. Here I won't touch that this concepts part into details, but whatever concepts I'm using in the problems will be discussed. This is not a theory class, it's mostly a problem solving session to help with your assignments, to help with your exams. That's the main motive of it. So this is week one, and here, as I already said, most on the basics question related to that will be discussed, and some few odd questions related to CMOS inverter, right? And then we have from next one CMOS in next week we'll have CMOS inverter, which we'll discuss thoroughly. Now some guidelines which I'll be laying out almost every week. So first of all, the first guidelines is you should join with the authentic usernames. I don't need your real names, but at least the names should be not be fictitious or inappropriate. So anyone having some inappropriate usernames will not be added to the session. That's something that's pretty clear to all of you. The second thing is camera and microphone etiquette. First of all cameras must be kept off all the time. No need to turn on your cameras, and microphones should be muted during the session. Whenever I'm solving a problem or whenever I'm saying something, microphones should be muted. Regarding the questions and doubts, I'll provide ample time for you guys to ask in your doubts. Whenever I finish solving a particular problem, if you have some doubts, if you have some queries, you can raise your hands or you can type in the chat box. Chat box will always be open. You can ask any doubts, any queries in the chat box. And if you feel like you are not able to ask your doubts in the chat box, you can always raise your hand after a particular problem is solved, or anytime you can raise your hand. I'll ask you guys to then I'll ask you to unmute yourself and you can ask your doubts. Since at start the role is quite high, try to use chat box feature only. But if you are comfortable with the uncomfortable with this chat box, you can always raise your hand, ask for permission, and I'll allow you to ask your doubts. And one thing to bring to your notice that this session is being recorded, right? So, and it will be made available immediately after I finish this class. It will be uploaded on my YouTube channel, and that link will be put on the weekly log sheet. I think that's not shared with you right now, but NPTEL team will soon share that weekly log sheet with you. Not only the recorded lecture, but also the PPT that I have here and the annotated PDF will be shared with you. And breaks part, so we have duration from 3 to 5 p.m. It depends on the number of problems, the time it takes to solve those problems, and how the class responds. So if the class is lengthy, 2 hours is pretty lengthy, but we might need some breaks in between. These are small breaks. We might have some short breaks in between, and some 2 to 3 minutes breaks we can have. And if some of the questions remain unanswered, you can always reach out via email. So I think I'm pretty clear with my guidelines. If you have any doubts among these guidelines, please ask or raise your hand if you have any doubt. If you have any doubt regarding the problem solving session or how this will work, anything, you can ask right now. You can raise your hand and you can ask. Okay, thanks. Yeah. Now, one thing I need to ask. Yeah. Can you guys raise, how many of you are from BTech or from bachelors? Can you raise your hand? Okay, right now you are in your bachelor's, yeah. Let me just check how much. Okay, 36, 36. So around half of the class. I'll just say it once again. How many of you are from your bachelor's or doing bachelor's right now? Okay, okay. So almost 50 to 60% of the class is from bachelor's. That's pretty good. And you can lower your hands, all of you. You can lower your hands. Yeah. And how many of you are from masters? Okay, okay. So 10 to 20%. And I assume anyone from, you can lower your hands, please. Anyone from industry or some other part? Okay, that's fine. Yeah, you can lower. So mostly we have a bachelor's audience here. So anyways, I'll mostly align into that direction. So this week, as I already said, this week is pretty basic because only basics were discussed in the course, and also the assignments that I saw. Assignment one was pretty basic. I'll try to increase the level of the problems from the next solving session, that is week two, that is on the next Sunday from 3 to 5 p.m. From there on, the level will definitely go higher. So now we have the first problem of today's live session. Let me just annotate it. Yeah. So this is the first problem which states that in a CMOS structure, again requesting all of you try to be on time. I don't have any problem. You can join any time, but it will be better if you join at time. That is 3 p.m. I do typically start at 3:05, but you can always join at from 2:55 because I already start the session at 2:55. I can admit you anytime, and at that time you can always ask your doubts. So it's the first question that we have here is in a CMOS structure, the NMOS transistor operates in the saturation region when option A VGS greater than VT and greater than VGS minus VT, option B VGS less than VT and VDS less than VGS minus VT, option C VGS greater than VT and VDS less than VGS minus VT, option D VGS less than VT and VDS greater than VGS minus VT. Anyone? Or type in chat box only, no microphone, only in chat box. Anyone knows the answer to this question? Yeah, thank you. So it's option A. So transistor MOSFET and MOSFET operates in saturation when VGS is greater than VT and VDS is greater than VGS minus VT. So let's just ask some basic questions here. Only use chat box, strict guideline. Uh, Question is, in saturation, ideally, how does a MOSFET behave? And MOSFET, what does MOSFET behave like? In saturation, how does a MOSFET behave? Exactly. It's the ideal condition, right? Current source, constant current source, exactly. When you say a constant current source, you are varying some voltage. Which voltage you are varying? And you are saying it's a constant current source. Okay, anyways, now the second question I would like to ask, yes, VDS, thank you. The second question regarding this I can ask. So we said this, it behaves as a constant current source in saturation, ideally, but there are some non-ideal effects. Can you name some of them? Yes, channel length modulation CLM. Okay, so we have so I have made some symbol. What is this symbol of? Only chat box, please. That's a request from my side. And Moss. And what is this terminal? This terminal. So gate. What is this? This. What is this? Okay. Some of you are saying source. Some of you are saying drain. But most of you have said source. Let's see. And what is this? This is drain. Uh, one of one of the student has written drain and source are interchangeable. How many of you agree with him? Drain and source are interchangeable. Drain and how many of you agree with that guy? Drain and source are interchangeable, so I can interchange them. So people who are saying they are interchangeable, so what decides whether a particular terminal is a source or drain? So what is the criteria? Thank you, but you can always use chat box. So these are the initial sessions. Attendance is quite high, so I don't want people to jump in the microphone. Sorry about that, but it's how we operate. Biasing, yeah. So the people, I think some of you are clear with the concepts. With the MOSFET, we have what should I say? The source is the symmetric structure, as one of you, the student has rightly said, and it is the voltage, the biasing, as you have said, that decides whether a particular terminal is a drain or source. In an N MOSFET, if a terminal is at a higher voltage, that is termed as drain, and the lower one is termed as source. In P MOSFET, it's vice versa. The source is at higher potential and the drain is at lower potential in PMOS. In NMOS, drain is at higher potential and source is at lower potential. So always remember, this one is gate, this is drain if it's at a higher potential, this is source if it has a lower potential, and current in NMOSFET flows from drain to source. Is that clear? Yeah. Always keep this thing in mind. The source and drain are based on the voltage applied. Now question 2, I think this one is directly from your lecture. The two types of device scaling are dash and dash. Option A, constant field scaling. Option B, constant length scaling. Option B, constant field scaling, constant current scaling, voltage scaling, and option D, constant field scaling and constant voltage scaling. Anyone? And only in the chat box. Answers only in the chat box. Yes. So directly from your lecture. So it's option D. Nothing to add in here. Now question number 3. So I have marked this. So that means I would like you guys to solve it first at your place. Type in your answer. If sometimes see, most of the questions are theoretical, sometimes you will not be able to answer directly, but what you can do is you can directly type in your answer in the chat box, and after some 4 and 5 minutes I will show you the solution. So the question reads as, with the knowledge that mu p, okay, before you solve it, what's mu p? Can anyone tell me what's mu p and mu n? In chat box, mu p and mu n, mobility is correct. So how do you define a mobility? Yeah, mobility of holes and electrons. So what is mobility exactly? Yes, ease of movement of charge carriers. Yes, ease of movement. So it's simply, you can directly guess it from the definition. This, what should I say? The name itself, ease of motion. Correct. So it's ease of motion. So the question states that with the knowledge that mu p is equal to 0.4 times mu n, what must be the relative width of n channel and p channel devices if they are to have equal drain currents when operated in saturation model with overdrive voltages of the same magnitude? Can So I would like you guys to solve first. So I'll give you some 3 to 4 minutes, and after that I'll show you the solution. You guys can do it, yeah. Some of you have already done it. I'll just confirm whether that answer is right or wrong after I show the solution. So try to solve it at your own place right now. So some of you have written the answers. It's fine. I think now I can show the solution. So what we have here is we are given this with the knowledge that mu p is equal to 4 times mu1. What must be the relative width of n channel and p channel devices if they are to have equal drain currents when operated in saturation model with overdrive voltages of the same magnitude? So overdrive voltage, first we should see what is this overdrive voltage. This is equal to VOV and this is equal to VGS minus VT. So overdrive is simply VGS minus VT. Now the condition that we have here is my drain to source current of n channel is equal to drain to source current of p channel. The magnitude is same, and then I can write, and it's in saturation. Both of them are in saturation, and I know in saturation my current is equal to k n dash by 2 wn w by l n. Now two terms I have written here. First of all is kn dash. What is this called? Only in chat box. Answers only in chat box. Kn bar. What is this kn star? What is this called? This term. It has a particular name, and it's equal to mu and cox, but it's called, there is a particular transconductance, but there is one more term before that, dash transconductance. Yes, process transconductance. Thank you. And the second term is W by L. What is this called? Aspect ratio. Thank you. So Kn by WL, and its VOV square is equal to Kp by 2 W by L P VOV square. Then this term and this term cancels since Kn bar is equal to, okay, 2 and 2 goes, L is also same. Then we have Kn bar Wn is equal to Kp bar Wp, and as someone rightly said, Kn bar is equal to mu n Cox Wn mu p Cox Wp. This will go, that implies Wp by Wn is equal to mu n by mu p. Mu n is equal, mu p is equal to 0.4 times mu n, so it's 1 by 0.4 and it is equal to 2.5, as most of you have done it rightly. So the correct answer to this question was 2.5. Now, yeah, in a particular technology L is same. Yes, it's perfectly safe to consider when not given, because in always in a particular technology you keep the length same and you mostly play with the widths. You will see in the coming lectures when you do the sizing problem, or have you seen that sizing issues? So you will definitely see the sizing of transistors. You keep the length fixed and you change the widths. Yeah, it's pretty safe to consider here. Yeah. Now the next question, it states that an n-channel device has Kn bar equal to 50 microampere per volt square, Vt equal to 0.8 volt, and W by L equal to 20. The device is to operate a switch for small VDS, utilizing a control voltage VGS in the range of 0 to 5 volt. Find the switch closure resistance RDS and closure voltage VDS obtained when VGS equal to 5 volt and ID equal to 1 milliamps. Recalling that mu p is equal to 0.4 mu1, what must be the W by L for P channel device that provides the same performance as N channel device in this application? So first of all, we need to calculate RDS, and then we need to calculate the ratio of the widths. So what I have here is an n-channel device having these parameters. So yes, you will get the PDF and PPT, both of them. But I think they have not shared the weekly log sheet as of yet. But they will be available to you by maybe in the coming days. So I'll show you, yeah, what is RDS. So RDS is defined as 1 by Kn bar W by L n times overdrive voltage, right? Basically, how this expression is arrived at. So when we have small VDS, my drain to source current ID is equal to mu n Cox W by L VGS minus VT times VDS. This derivation you can look in your book or some book or maybe online. So if you want to look at the derivation of this part, you can refer to a book by Sir Ryan Smith, or you can simply go to Google and type. You can always check the derivation. So this is for small VDS and GDS. So GDS is defined as ID by VDS, and it's equal to mu n Cox W by L VGS minus VT, and the reciprocal of GDS is RDS. So this is your RDS, right? Got it? You can say that for small VDS, you can neglect the second term. Yes, but there are other ways to arrive at this equation as well. You can say this is a linear region simply, the triode region, right? And it behaves like a resistor. I think now you can connect the dots. So we are simply required to find the RDS and just plugging these values that we are given. So it is equal to RDS equal to 1 by Kn bar is 50, then into 10 raised power minus 6. So always one word of advice, always be careful with the units, the dimensions they are in, and in what system they are in. Always try to remember them, and always try to write them, because sometimes, most of the times when you do the numericals, we tend to make these mistakes. So be cautious with the units. Then the W by L is given as 20, and my V overdrive is VGS minus VT. So it is 1 by 50 into 10 raised power minus 6, 20. VGS is 5, and VT is, how much is VT? VT is 0.8. So it is, if you do the maths, it comes out with 238 ohms. Can someone confirm? Can someone do the calculation for me and check whether this is correct? Okay, thank you. In this way, you are following simultaneously. It will keep you engaged in the lecture. Now, the second part is what must be Wi by L for P channel device that provides the same performance as N channel. So simply what we have here is mu P is equal to 0.4 mu N. So for same performance, we'll just simply multiply it by 2.5 as we have done it in the previous question. So W by L P is equal to 2.5 times W by L N. So it is 2.5 multiplied by 20. So it is 50 because of this condition. Now I have a question, that is question number 5, that I would like you guys to solve first. It will take around 5 to 6 minutes. So the question is, consider a CMOS process for which L min is equal to 0.8 microns, Tox is equal to 50 nanometers, mu n is equal to 550 centimeter square per volt second. So unit of mobility is centimeter square per volt second, and Vt, that is the threshold voltage, is 0.7 volt. So you need to find the Cox, that is oxide capacitance per unit area, Kn bar, and then you have the second part for an NMOS transistor with W by L equal to 16 by 0.8. Calculate the values of overdrive, VGS, and VDS min needed to operate the transistor in saturation region with DC current of 100 amps. And the final question is for the device in B, that is part B, find the value of overdrive voltage and gate source voltage required to cause the device to operate as a 1000 ohm resistor for a very small VDS. So this is silicon dioxide, not silicon dioxide. So oxide, for silicon oxide you can consider silicon oxide. So I hope you know the relative dielectric constant of silicon dioxide. How much is it? These numbers you should remember. No, it's not 13.6. 13.6 is for, no, it's not 13.6. It is 3.9. For silicon dioxide, it's 3.9. And by the way, what is the dielectric constant for silicon? Anyone? Does anyone know dielectric constant for silicon? Yes, 11.7. Thank you. 3.9 for, take epsilon ox equal to 3.9. Your answers will be confirmed only after I show the solution. Till then, you can always look if you have done it correctly or incorrectly. I'll just wait for a couple of more minutes and then I can show you the solution. You can always try. Keep trying. So let me just show the solution. So first of all, we need to find this oxide capacitance and the Kn bar, that is the process transconductance. So your Cox is simply equal to your epsilon ox by Tox, and your epsilon ox is equal to epsilon R of SiO2 times epsilon naught, that is the permittivity of the space, and divided by Tox. So as I already said, epsilon R for silicon dioxide is 3.9, and permittivity of free space. Can anyone tell me what's the value of permittivity of free space? What is the value? Yeah, thank you. It's 8.85 into 10 raised to power minus 12. And what are the units in the chat box, please? What are the units? 8.85 into 10 raised to power minus 12. Units, always a sign of units. Farad per meter, thank you. So it's farad per meter, and the Tox here we have is 15 nanometer, so it's 15 into 10 raised to power minus 9. So let's do the math and see how much it comes out to be. So it's 3.9 into 8.85. How much is it? Let me just take out the calculator. 3.9 into 8.85 divided by 15, 2.3 into 10 raised to power minus 3 farad per meter square. Yes, do not forget units. 2.3 into 10 raised to power minus 3 farad per meter square, and Kn bar is equal to Qn times Cox. Your mu n is equal to 550 and 2.3. Let's just convert into centimeter square because my mobility is in centimeters. 550 and multiplying by COX, so it's 2.3 into 10 raised power minus 7. It comes out to be 1.265 into 10 raised power 4 ampere per volt square, and that is equal to 12.126.5 microampere per volt square. You can always do the maths. And now this was part A. Now this is part B, which states that for an NMOS transistor having W by L equal to 16 by 0.8, calculate the values of overdrive voltage VGS, VDS min needed to operate transistor in the saturation region with a DC current of 100 amps. So required is, we know that in saturation ID is equal to Kn bar by 2 W by L V overdrive whole square, and it is given to be 100. It is going to be 100, and Kn bar we found out it's 126.5 divided by 2. W by L is 16 by 0.8, and then V overdrive square. If you do the math, it comes out to be V overdrive square comes out to be, let me just redo it. It comes out to be, V overdrive square comes out to be 0.07905. Can anyone confirm? Is this correct? Okay. Now V overdrive square is this, and then V overdrive will be equal to plus minus 0.2812 volt. So now we have two values for V overdrive, 0.28 and minus 0.28. Which one should we take? Positive. Yes, it's positive because we are having an N-channel device. So V overdrive voltage is equal to 0.2812, and my VGS will be equal to VGS minus VT is equal to 0.2812. That implies VGS is equal to 0.28 plus VT is how much? 0.7. So VGS comes out to be 0.9812. So this was my part B. For part C, RDS, which we saw earlier, is equal to 1 by Kn prime W by L and V over drive. And RDS is given to be 1000 as per question. You can see here 1000 by 1 by 126.5 into 10 raised power minus 6, 16 by 0.8 multiplied by V over drive is 0.28, 0.2812, and ultimately V over drive comes out to be 0.3953 volt. And from this you can easily find VGS simply by adding the VT. Any doubts in this question? Thank you. Now we have question number 6 of today's live session. This is some basic stuff. I wanted to just give you a glimpse of the economics part of it. Some basic numbers. I don't think whether they'll have some technological significations and all. So we have, suppose, the NRE cost, so non-recurring engineering cost. So it's a one-time engineering cost that is required to develop some technology. For getting the first prototype of a 50 million transistor chip is $10 million. Calculate the NRE cost if the total product volume of the chip is estimated to be 100K or 100 million. So we have option question A, which is 100K. So what we are given is NRE cost, that is equal to $10 million, that is 10 into 10 raised power 6 dollars. Now in the option A, my chip volume is 100K. So my NRE cost of chip is volume by, this is NRE cost divided by volume. So it comes out to be $100. Now when my volume increases, what is my NRE cost? That time we have 100 million. So it is cost, that is 10 into 10 raised power 6 divided by volume, that is 100 million. So it is $0.1. So as the volume increases, my cost of chip goes down. This was just to give an idea. This is, I don't think this is somewhat connected to your coursework. Now question number 7, it says that the truth table which accurately explains the operation of CMOS NOT gate is, I have these 4 options. So answers only in chat box. Can anyone tell me which is the correct answer? This is a non-recurring engineering cost. That is the cost that is there for developing a particular technology. I just wanted to give you a flavor of it. Don't worry about it. It's nothing to do with your coursework. Anyone? What is the correct answer to this question? Only in chat box. Answers only in chat box. Yeah. So it's option D. So what is a NOT gate? What is another name for NOT gate? Yes, inverter. Very, very important from a digital point of view. So in CMOS inverter, which is typically made like this, this is your PMOS, this is your NMOS. So when your input is low, when your input is low, your output is high. When your output is high, your input is low. So when your input is low, PMOS is on and NMOS is off. So as a result, this VDD is connected to your output node. So V out is equal to VDD. So and PMOS is on. When output is high, input is high, V in is high. This PMOS is off and NMOS is on, and we, or as a result, this output node discharge gets pulled down to ground, and we have output equal to 0. So PMOS is on for input 0, NMOS is off. For input 1, PMOS is off, NMOS is on. Output high, output low. We will see inverter at least for next 2 weeks in detail, where we'll see the sizing problems, the noise margin problems, the propagation delay problems over the next 2 weeks. This week I have just touched a portion of it, but yeah, maybe towards the end you can ask. Let's just try to finish this part, and then I can definitely come back to you. Just remind me at the end. Now, question number, I think I already shown the answer to it. The below circuit acts as, this is inverter. This is PMOS bubble, which signifies a PMOS. This is NMOS. What does MOS stand for? Yeah, it's metal oxide semiconductor. Thank you. Hmm, anything else? So, which book you are referring to? Anyone in the chat box? Are you referring to any books or simply the nectar notes only? Yeah, no notes. So I'll suggest one of the students has said that notes, definitely you should follow them. Professor Sudhir Gupta has really taught it well. First, the lecture notes, the lecture notes, followed by the book from Rabbi. That is the best book out there. So you should refer to that. Yeah. Now, this was question number 8. After that, we have question number 9. So now we have a question which says that determine the resistance of polysilicon wire shown in the figure below. The sheet resistance is 4 ohm per square. So we have to find resistance of the given wire. Given is the sheet resistance equal to 4 ohm per square. Now how will we calculate this? Digital integrated circuits by Jan M. Rabai. I think he's from UCB, right? Let me just digital integrated. You can look at this book. A pretty good book, very, very good book. I shared the book name in the chat box. So what we have to do is here is we have to find the sheet resistance. Sorry, we have to find the resistance of the wire given as the sheet resistance. So how will you do it? So resistance of this wire will be equal to the sheet resistance multiplied by number of squares. So how will we find number of squares? We will divide it into segment. So this is one horizontal segment, this is another horizontal segment, and this is your vertical segment. So sheet resistance is 4 ohm per square. Number of squares is, first we'll look at this. So number of squares that will be made out of this horizontal segment is 19 by 3, plus this one is 11 lambda by 4, plus this one is 19 lambda by 3 lambda again. So this is equal to 4 ohm multiplied 4 ohm per square multiplied by 15.416 equal to 61.67 ohm. So the resistance comes out to be 61.67 ohm. Got it? So if I'm not mistaken, I think you have taken up the area, right, and then multiplied by the sheet resistance. That's what I have done, right? You got 632 by doing that. Yeah, I think this is the first time you are looking at this problem. I understood, yeah, understood. Nothing to worry about. Yeah, I hope you got this, how we have done it, right? So now the next question of today's live session, which is question number, this was question number 9, now we have 10. So I would like you guys to solve it first. So we have the question. Consider an NMOS transistor with the following parameters: oxide thickness 6 nanometer, length 0.4 microns, width 0.36 microns, LD and LS equal to 0.65 microns, C0 is equal to 3 into 10 power minus 10 farad per meter, CJ0 is equal to 2 into 10 power minus 3 farad per meter square, and CJSW0 equal to 2.75 into 10 power minus 10 farad per meter. Determine the zero bias value of all capacitances. Your overlap capacitance, junction capacitance, sidewall capacitance, find them. I'll just give you 5 minutes. You can do it at your place and I'll show you the solution. Kindly turn off your microphones. Can you please turn off your microphone? Yeah. So let me just show you the solution. So we first compute Cg, or we can term it as Cox, that is equal to epsilon ox by Tox. Your epsilon silicon dioxide, we assume it's 3.9 into 8.85 into 10 to the power minus 12 divided by your thickness of oxide, that is 6 nanometer, and this thing comes out to be, if you do the maths correctly, it comes out to be 5.8 into 10 raised to power minus 3 farad per meter square, and in terms of femtofarad per micrometer square, it comes out to be 5.8 femtofarad per micrometer square. So your 1 femto is 10 raised to power minus 15, right? Now CGC, gate to channel, equal to Cox W into L, right? So your Cox is 5.8 femtofarad, that is 10 raised to power minus 15 per micrometer square, and your W and L are also in micrometer, so we'll just write 0.24 into 0.36. If you do it correctly, it comes out to be 0.5 femtofarad. Are you guys following? Can anyone? Yeah, thank you, thank you, thank you. And now we have overlap capacitance, that is CGDO equal to CGSO equal to C0, that is in farad per femtometer. I just wrote the units here, no need to write here, multiplied by W. C0 is given, it's 3 into 10 raised to power minus 10 multiplied by W, that is 0.6 into 10 raised to power minus 6. So it comes out to be 10 raised to power minus 16, that is 0.1 femtofarad. Now we have the junction capacitance, that is equal to CJ S equal to CJD equal to CJ0 multiplied by W multiplied by LD, that is equal to CJ0, no, this is CJ0 is equal to 2 into 10 raised to power minus 3 multiplied by W is 0.36 into 10 raised to power minus 6 multiplied by L, that is LS multiplied by LS equal to LD multiplied by LS equal to LD, that is 0.625 into 10 raised to power minus 6. If now let's calculate, and it comes out to be 0.45 femtofarad. Next one is side wall capacitance, that is equal to CSW equal to CJS, that is CJSW 0 multiplied by perimeter, that is equal to W plus twice LD. So it is CJSW 0 is given as 2.75 into 10 raised to power minus 10 multiplied by W is your 0.36 plus twice LD is your 0.625. So it comes out to be 2 point, if you do the maths correctly and take care of units, it comes out to be 0.44 femtofarad. Is it clear? I think capacitance is always COXWL, that is overlap capacitance, this one CGSE, not overlap junction and sidewall capacitance. If you have any doubt, you can check this, what should I say, um, Rabbi chapter 3. You can find this thing in Rabbi chapter 3, or you can always refer to your notes. I think it's also in the notes, right? I hope it's clear, right? Now, question number 11. It states that for a CMOS process, the following parameters are valid. Assume in saturation device. So device is in saturation, velocity saturation, and my parameters are given like this. So we need to find, assuming Kn equal to Kp, we need to find the switching threshold voltage Vm, and we need to comment on the VTC of the inverter. What is it from the Vm value? Before I proceed, so I have the question here. So what is this? In chat box only. What is this called? Kn. Which transconductance? Process transconductance or device transconductance? And only use your chat box, please. Yeah, it's device transconductance. This one is your process transconductance. This one is your device transconductance. Just multiplied by a factor of W by L. So now the question asks us Kn. So Kn is equal to mod of Kp, and Kp is negative number. I hope you are aware of that. And now what we have here is we have the expression for Vm. Vm is your what is Vm called? Switching threshold, the tripping point of inverter as well. So Vm is equal to Vtn plus Vd sat n plus R times Vdd plus Vtp plus Vd sat p by 2. This is also 2 divided by 1 plus R. So I think this equation is also derived in your lecture notes, and if not, you can refer to equation 5.3 from Rabbi. Equation 5.3 Rabbi. So R, now let's compute R. R is equal to Kp by Kn, Vd sat P by Vd sat N. Since Kp is equal to Kn, once we divide Kp by Kn, the vector comes out to be 1. But since Kp is negative, it will be minus 1. And Vd sat P is given to be minus 1. And my Vd sat N is equal to 0.63. So this comes out to be 1 by 0.63, that is 1.587. Now plug this value of R into this equation, we'll get Wm equal to Vtn is 0.7, Vd sat n is 0.63 by 2 plus R is 1.587, we just derived it. VDD is how much? VDD is 3 volts plus VTP is minus 0.7 and VD sat is minus 1, so it's minus 1 by 2 divided by, whole thing is divided by 1 plus 1.587. And once you do the maths, you get Vm is equal to 1.497, that is approximately equal to 1.5 volt. So Vm equal to 1.5 volt, what does it signify of the VTC of CMOS? So what we can say about the VTC of the CMOS if Vm comes out to be 1.5 volts? Have you guys looked at voltage transfer characteristics in your lectures? VTC, that's called. So if you have seen that, so if my tripping point is 1.5 volt for a VDD of 3 volt, what we can say about this? We can say the characteristics, yeah, half exactly. So in other way, we can say characteristics are symmetric, right? Characteristics are half of VDD means characteristics are symmetric. Now I have this question. This is exactly like question 11. So I would like you guys to do it first. For a CMOS inverter, find the switching threshold voltage given if the transistor is in saturation, lossy saturation. Ignore CLM. Use the following data if required. By the way, I think at the start of the lecture we discussed this CLM, right? Channel length modulation. What does channel length modulation do? How does it impact my characteristics? Can anyone? First, uh, you can always type in chat box or channel length modulation. How does it affect my characteristics? Anyone? How does CLM impact my increases ID? With VD it increases. But how? But why? Uh, if you are aware of that, good. So this is a basically short channel effect. From the drain side, when we increase the drain voltage, yeah, lambda factor. That is basically the approximation of it, where lambda is your channel length modulation factor, and you get that factor multiplied to your drain current equation, and you have this slope in with increase in VDS. You don't have a constant current; you have a slight slope in there. Basically, when we give the drain voltage, we increase the drain voltage in saturation. My current should ideally be constant. But what happens is my depletion region with increase in the current, sorry, with increase in the voltage increases from the drain side. But in long channel device, this doesn't impact that much. But however, in a short channel device, my effective channel length decreases. And once my effective channel decreases, my current increases, as you can see from the equation. And then we make some approximations and we get to this equation 1 plus lambda VDS. I think this is also, I think this is not discussed in detail because it's mostly from a modeling perspective. But first order approximation, you can use this equation. And have you seen this drain induced barrier lowering? DIBL. It's another short channel effect, yeah. What it does, lambda here right now lowers the threshold voltage. Correct, correct. Lowers the threshold voltage. As the VD increases, I don't want to go into the physics part of it, so it will be digressing from the lecture or from the problem solving session. So if you want to look into more details, yeah, reduces the control of the gate. We want gate to be the master of our device. It reduces the control gate because it lowers the barrier from the source side. My drain bias affects the barrier from the source side, and as a result, my carriers get injected from the source with the lowering of the source barrier, which increases my current and thereby decreases the threshold voltage. If you want to go into physics side of it, you can always refer to these beautiful books, that is SMZ, Physics of Semiconductor Devices by SMZ, and also Semiconductor Device Fundamentals by Robert Parrott. These are the device that gives a device fundamentals part of it, but that will be digressing from the coursework and I don't want that. But if you want to know more about these devices, the short channel effects, the physics part of it, you can always refer to these books, the semiconductor device fundamentals, which is more fundamental, which is more I will say well suited for BTech or early master's level. SMC is also really good, but it doesn't cover I think you should have one should have a prior knowledge to cover to refer to SMC, but that's also a really good book. You can always refer to those two books. So this is exactly anyone has done question 12. And one more thing, one of the student asked me, can you please share the PDF after class? So PDF, PPT, and the lecture recording will all be shared in a weekly log sheet, and the weekly log sheet will be shared in the SOAM portal by the NPTEL team. I don't have access to that, but that will be shared, I think, within 2 or 3 days. Has anyone done this question? I think this is quite similar to the previous question. If you have done it, you can always type your answer in the chat box. So has anyone done it? I think this was pretty similar to the previous question. You were just plugging the values. So I'll just show you this part of the solution, and maybe in the next class you can tell me what was the answer, because none of you have done it. So again, you have to do it like this. So it will be equal to Vm is equal to Vtn plus Vd set n by 2 plus R times Vdd plus Vtp plus Vd set p by 2 divided by 1 plus R. You can compute R, and R will be similar to the previous value because W by L here is also same. So R will come out to be as, oh, I think it will be different, right? KPKN, yeah, no, KPKN is same. No, it will be different, it will be different. KP, so R is equal to KP by KN times VD set P by VD set N. KP will be equal to W by L P KP bar by W by L N KN bar. W by P L, this W factor is same. KP and KN are different. And then we have this minus 1 by 0.63. KP, this is also negative, so the term will be positive. Then you can follow the question and plug this value in this one, and you can get the answer. Do tell me your answer in the next class. Now, the question is this regarding the solution of this PPT. Everything, I think I'm telling this for the third or fourth time, but I guess you joined late. Everything will be shared, the recording, the solution, the PPT in the weekly log sheet, which will be shared to you guys by the NPTEL team this, on the SWAYAM portal. So everything will be made accessible to you guys by the team members. So I guess that was all for today's live session. Next session, next 2 weeks, we'll mostly concentrate on the CMOS inverter part of it. I guess there was some question regarding something. Is that student still in the class? Kindly raise your hand and please ask your doubt. So this is similar to the question number 11. So I have deliberately not shown to you this guys because the method was same. It's just the physics. I mean to say the values just changed. You just needed to plug in the values and do it. So you can take this as a take home question and we'll definitely discuss this question again next time. I want you guys to solve it first. That's why I haven't shown the solution of it. Yeah, everything will be shared. I'm telling you guys, everything will be shared. My job is to just put it into, my job is to put it this lecture recording, the PDF, the PPT into the weekly log sheet. The link of weekly log sheet will be shared by the NPTEL team members. That's not under my control. They will definitely share in coming week. So, regarding question number 11, yeah, someone is asked, can you please repeat question number 11? So basically, the question is for us. That's not up to me. I don't have access to that thing. I don't create any groups and all. My job is limited to this 3 to 5 to show you the lectures. If you have any doubts within this lecture, you can always ask me. If some doubts remain unanswered, you can always hit an email. Or if there is some doubt regarding the question, this lectures from the professor, you can always use the Google forum. No groups, no channels will be created separately for this purpose. So the one of the student has asked question 11 for a CMOS process the following parameters are valid assume in saturation device assuming the device is in saturation velocity saturation we have the following parameters and now we have one more assumption that Kn is equal to Kp that is device transconductance is equal to of PMOS is equal to NMOS. Now we need to calculate the switching threshold. So we have the switching threshold which is given by this equation Vm equal to Vtn plus Vd sat n by 2 plus R times Vdd plus Vtp plus Vd sat p by 2 divided by 1 plus R. This is equation 5.3 of Rabai, the book I have mentioned earlier in my class. So R is computed by Kp by Kn multiplied by Vd sat p by Vd sat n. Since Kp is equal to Kn, this thing will go, but the factor -1 will remain there because we take Kp to be negative and Vd set P is equal to -1 here and Vd set N is equal to 0.63. When you do the math, it comes out to be 1.587. Now Vm is equal to zero point 0.7 because Vtn is equal to 0.7 plus 0.63 by 2 because Vd set N is equal to 0.63 plus 1.57 because R is equal to 1.57 multiplied by Vdd that is 3 plus Vtp that is minus 0.7 and Vd sat P is -1 so it is -1 by 2 and divided by 1 plus R so it is 1 plus 1.587 so this part and when you do the calculation the answer comes out to be 1.497 that is approximately equal to 1.5 volt that is half of your VDD so the tripping point is nearly at the center of the 0 to VDD scale which means the characteristics are somewhat symmetric or rather I should say symmetric. So is this clear to the COX and CDP are connected in series? Where? I haven't used anything right there. Okay, you are telling about the capacitance if you do. But I haven't used that thing anything here. Pulkit. So maybe yours the question is something different. Because there basically COX is your capacitance between the gate and the gate. We have the gate oxide and then we have metal oxide semiconductors and there is a depletion charge and depletion charge acts also like as a capacitor. So these two capacitors share the same internal node and once they share the same internal node these are bound to be in series, right? you're telling about the schematic of this, we have this MOS cap, so we have this C aux and we have this C dep, and also we'll get this inversion, C inversion. I will not go there. So this thing, because they share the same internal node right here, that's why they are in series. So this is an interesting question. At least it's from a device point of view. You can refer to the book. If you want, I can tell you the best part. You can refer to this lecture. Lecture series. I don't exactly remember the name. Let me just check. Just stay there. I hope the doubt got cleared, right, Pulkit? Mhm. Now I have that. Yeah, you can refer to this lecture series by our professor at IIT Kanpur, Introduction to Semiconductor Devices by Bakir Mazari. Let me just, if I can share the link with you guys. I'll just type the name, Introduction to, it's a pretty good series, lecture series. So those people who are very much interested into this field, particularly the UG students, you can refer to this lecture series by our professor. And you can also refer to, if you want just to get overview of the things, but for that I'll suggest you should have the background. You should have read the at least some book prior to that. You can always refer to this modern semiconductor devices, the book name modern semiconductor devices for what was the book name? I forgot the book name. The author is Professor Chen Ming Hu from UC Berkeley. The book name is, I'll tell you the exact book name. The book name is book name is Modern Semiconductor Devices for Integrated Circuits by Professor Chen Ming Hu. That is a really good book, but that's for overview. If you want to get the overview of the things, if you have the prior knowledge, that book is ideal for you. But Parrot and the lecture series you can refer to get to know the idea of semiconductor devices. Any other doubts? Any other queries? Yeah, Ramakrishna, I can see your hand. I just want if there are any other queries or questions.